So in an earlier lecture, we were looking at the vertical well under saturated oil, and we saw this was like a radial geometry. Okay, we said it was a radial geometry. And we say, well, the bottom hole pressure is always going to be within the undersaturated region area, either because it's, the pressure is high enough, or because, the envelope is very small the saturation region is very small. So we did an experiment where we lowered the pressure gauge, and then we were changing the rate, and we were able to take a series of points, and actually what we saw is that the relationship between those, between flowing bottom hole pressure and oil rate at standard conditions, is linear, and it followed this relationship, which is a very powerful equation, very simple to use, and I just need one test point. But one of the deficiencies is that actually I need to have a producing well to be able to know the J. Another problem we have is that, for example, for the design phase, is that we really don't have yet the well, so we cannot make any testing, and we cannot see how it behaves. And for planning and design of the well, we're interested to see what's actually affecting this J, and how can I make it larger, because I'm interested to maximize the production. Another thing is that, well, I also need to know future performance, what will happen with that curve in time. So I need to make sure what's affecting that and how it can change in the future. So we are going to follow now a different approach to find out that equation for this configuration. We are going to, which I mentioned earlier, which was we are going to take conservation equation, and we are going to start to apply to a particular geometry, to a particular case, and assuming doing some simplifications, then we are going to arrive to an analytical expression of the IPR, of this PWF versus QO. And then we can compare it with the one we found here and see how different they are, and what things does the J has inside. So for that, we're going to use the equation. The main equation we're going to use is Darcy's law, okay, which tells you that velocity of a fluid going through a porous media, where that's the only fluid you have, is equal to permeability divided by viscosity of the fluid times dp dx, and this is if I'm talking about a slab of porous media. Okay, where the main flow is in one direction and x is also on that direction. Okay, so that tells you essentially that, well, the pressure drop across that slab or on that porous media is actually depending on the velocity. If I have a higher velocity, I will have a higher pressure drop. Okay, and also it depends on the properties of the fluid, depends on the viscosity, how difficult or how many losses the fluid causes when it flows through it, and also depends on some property of the porous media, of the rock, that tells you how difficult it is through flow, how many obstacles, how do you have on this porous media. And just as a side note, here we have to the right a photo of Darcy taken from Wikipedia, and he was a hydraulic engineer working mainly with water supply systems, and he, at the beginning of his career, he worked in a city called Dijon in France. And then he went to other assignments in Paris, some other places, but in 1856 he retired to that same place, to Dijon. And then that's where he performed his experiments that became the base for this equation and for this law that actually changed and was an enormous contribution to society and to science. And he made a series of experiments, and he made, I think, a few reports, but this is the most famous report he had. I have here, I downloaded from the web. I think you can also, it's open source. And here to the right is the experimental setup he used for, so you see here, this is a column of sand, and he's flowing some water through it, and then he's measuring with this gauge, he's measuring the difference in pressure across the sand. Okay, and he died soon, a bit soon after that, 1858, he was dead. Okay, or he died. But and it actually in the report you don't see there are not many tests. There are only a few tests. So what we're going to do is we're going to apply this equation to our case, our well, vertical well with this radial domain, and we're going to try to simplify to see what do we get, what kind of equation we get. So the domain we're going to be working with is, this is our W, and here a longer, bigger radius called RE. Okay, and the well bore, let me just paint it completely, and we have something like that. Okay, so that's the domain where we're going to apply it, and we have a undersaturated oil. One thing important to notice is that we are saying that we are in steady state or pseudo steady state. Okay, that means that this term in the equation is going to be 0. And that is why we can use just this expression without looking at anything else, without looking at the accumulation, because essentially we are saying we are in these two regimes, then this one is not important. Okay, so another thing we have to be careful is that this V, we don't typically work with velocity, but actually we work with rate at standard conditions. So we have to find a way to convert between these two. So I can say that V is going to be equal to QO divided by the area that the fluid is going through, and now the equation also we have to change it slightly, because we now it's not anymore a linear, it's not anymore a slab, but it's a cylinder. So we have K over me dP dr, okay, because now we're looking at the radius, we are looking at this in this coordinate, okay, and we simply change it like that. And this rate, volumetric rate, is the local rate, which is in cubic meter per day or is in cubic meter per second, okay, but it's not in standard conditions, it's a cubic, it's a local conditions. And this area, well, this is the area that the fluid is going perpendicular to, okay, which if I make something like that, so this will be the area, and the area will be then is 2 pi r, that is the perimeter, is this all of this line that I have here, and then I multiply times the height times h. So then we are coming here, you see this equation now, this v is having an r here, that I have a derivative of r, a differential of r here, that I have to put them together. But QO still, I don't have QO. I'm working typically with Q. Working typically with QO. So how do I convert from QO to QO local? And for that, petroleum engineers use black oil properties. Okay, that they relate actually those quantities. Okay, and it's something, it's an approach very useful. So I have, imagine that I have at a particular pressure and temperature, I have some oil, and then I decide to take it to standard conditions. Okay, that remember we said is 1.013, 25 bar, and 15.56 Celsius. And what happens in that case, two things happen. So I have some oil, I will have some oil, and then I also have some gas that is going to come out of solution. Okay, so you can say that here you have some volume of oil at standard conditions, and here you have some volume of oil at local conditions. So I define the oil volume factor as BO as a function of pressure and temperature is going to be equal to the volume of oil at P and T divided by the volume of oil at standard conditions. So it's like a ratio of volumes, and this typically is greater than 1. Okay, so then that means that my QO, if I use Q here, QO will be equal to BO at pressure and temperature multiplied by QO at standard conditions. So that's actually the expression I'm going to use now on my equation. I'm going to say that V is QO times BO divided by 2 pi RH is equal to K over viscosity of oil times dP dr. Okay, now we and this, so the units of this BO, okay, if you see the units are in cubic meter per standard cubic meter. So essentially these are both cubic meters, so it's actually a dimensional, but it's very important, I think, to put the unit to make sure that it's, you know, what ratio of volumes is it comparing, okay? Because sometimes I forget that if it's standard over local or local over standard. So if you keep the units, it's important because it tells you what it is, what is it representing. So now I have to, now if I want to make an integral, right, because I have differentials, so I have to get rid of the integral, or I have to get rid of these differentials, and I have to make an integral between some place and some place. So for that, I try to put everything that has to do with pressure to one side and everything that has to do with radius on another side. So if you remember, this guy and this guy, the properties, they are actually a function of pressure and temperature. This guy is a constant typically. I'm assuming that it's homogeneous, has the same permeability. H is also a constant. R is a function of, is simply R, okay, simply a function of R. This is a constant, the 2 pi. But then what happens with QO? Okay, what happens, is it QO a function of radius? Okay, and now what we're going to assume here is that if you, for this approximation, we say that QO versus radius is actually simply constant until RE. That's the approximation. So QO is not a function of radius. Okay, it's simply a constant. That means that, remember that QO at standard conditions is almost like a mass flow. So it's telling you that the mass flow in any radius is going to be the same. Okay? And this approximation just has a side note. This is valid for steady state. Okay, because if you remember, in steady state, the boundary, actually here I'm saying that I have some process, or I have some injection, I have some influx that tells me that, well, I essentially am keeping that pressure constant at that boundary. Okay. While if for the pseudo-steady state at that boundary, you actually say I have no rate, it's simply a no flow boundary, it's simply zero. Okay, so this approximation won't work if you are in the pseudo-steady state. Okay, but don't worry, we will see later that, you know, that still applies. So what we do is that we then put the equation as 2 pi K over QO, and here we have dP, neo, BO, and on this side we have dr over R. And we need H, we're missing H here. 2 pi K H and QO. Now we need to integrate, as I mentioned, to get rid of these differentials. And from where do we integrate it from? So one thing we can say, well, we integrate from RW. Okay, there is not much to go. And at RW, the pressure is PWF. But then the upper bound, where do we integrate to? So we could say we want to integrate all the way to the boundary, to PE. But if you do that, you see that we will see that in the equation, actually we're going to get here, you get the impression or the intuition that this integral is going to give you the difference in pressure that you want, that we saw for the empirical IPR. Okay, it's going to give you this difference. So really, and so we should be doing it here until some reservoir pressure, not until PE. Another thing is that the boundary sometimes is difficult to know where it is exactly. So we will have to come in and try to guess the boundary, the pressure at the boundary. Okay. While reservoir pressure, if we do the integral until reservoir pressure, then simply to find reservoir pressure, we just have to shut in the well and let it stabilize, and it's going to give us that pressure. So instead of doing it until PE, we're going to make it until reservoir pressure. Okay, and then here I come with a hiccup, which is, well, I have to say until the radius at which I have reservoir pressure. Which it sounds like a big issue, but it's not so much of a big issue. So that means, if you remember our plot of pressure versus radius, and here we have RW and RE. Okay, you remember that it looks something like that. Okay, that's why we did our exercise, not exercise, but we did a thinking experiment of how it will look like. Okay, and reservoir pressure is the average, the volume average of that pressure. So is the integral, reservoir pressure is essentially the integral in volume of P dV. Okay, divided of course by the volume. Okay, so essentially here you have PE. This will be your PE is here, and this is your PWF. So reservoir pressure is going to be someplace in between, because it's when you shut in production, that's the pressure that you get. This is PR, and this is the R at which you have PR. So I'm not going to go through the derivation here, but I just want to say that for steady state, the R at PR is equal to 0.61 RE. It's located exactly at 0.61 of the external of the boundary radius. And that's simply requires some mathematical derivation, requires to calculate that integral, okay, but you will see that by doing that you'll find that number. So with this number now we can say, well, this part of the integral, this part 1, is going to be ln of 0.61 RE divided by RW. And that we can say is the ln of 0.61 plus the ln of RE divided by RW. And we can say that this is the ln of RE divided by RW minus 0.5. So that's this expression number 1. Now for the second part, which is, and you see now it's a bit taking shape, we know that this somehow the IPR will have all of these 2 pi kh, will have this ln, and then let's see what happens with this part. Okay, so let's look at this part now. Okay, this we call 2. So 2 is the integral of from PWF to PR of 1 over mu O BO dP. And we have to find out how these two, because you remember these properties, they are a function of pressure and temperature. So they are going to change, they are going to vary with pressure and temperature. It's F1 and F2, okay, 2 different functions. But we say that at reservoir, then actually T is constant and is equal to TR. That means that I don't need to include the temperature dependence, I can only include the pressure dependence. So if we're going to plot how it looks like, and these BO properties I can calculate from laboratory experiments, I can calculate from a correlation, some people came and they, for fluids in their fields, they make correlation and it's applicable for other fields in the world. Or I can do it with an equation of state in which, or a program in which I calculate this process. Essentially I simulate this process of taking from local to standard conditions, and then I calculate the BO. Okay, but essentially what you will see is that it looks something like that. So this is going to go like that, and at some point then I reach the bubble point pressure, and then it's going to start to go down. Okay, and this from here it will be the undersaturated. Okay, and this one to the left is the saturated. But remember, we are saying that PWF for our IPR and PR are essentially in this range. Okay, so then I'm only concerned about this part. So the main message is that pressure goes down, this goes up. So it has a inversely proportional relationship with pressure. The oil viscosity actually does the opposite. It's increasing, okay, because I'm getting everything packed up in the same, it's like it's getting more material, more mass in the same location, so everything is getting packed up, and then that's why the viscosity is increasing slightly. Then after I reach the bubble point pressure, then is starting to increase again. And that increase here is simply due to, because you have, when you take it, this is in saturation, so you take it, here is losing light components. Here is using methane, ethane, and then that's making the fluid actually heavier. Okay, it's making it more richer in heavier components, and then it's making it more viscous. So you have these two, but actually what we are interested is in the combination of both. Okay, we are interested in 1 over mu BO. And if you see there, what you will see before until the bubble point is going to be something like that. Okay, it's fairly linear. This is like linear relationship. Okay, so I have here some data I can show you. Okay, so here is pressure at a fixed temperature. Pressure is increasing all the way to 400 bar. Okay, this oil has a very low bubble point pressure, so everything here is essentially undersaturated. And here we have BO, and here we have viscosity, and here we have the 1 over the product of both. So here we have 1 over the viscosity, the BO times viscosity. Okay, and I've plotted here, and you see the relationship. This is a trend line which is linear, and you see it's not exactly 100% linear, but it's fairly linear. Okay, and you can plot, if you want, you can plot BO and viscosity. You see here, but you see here that it's bigger, and then it's starting to decrease, and here is actually smaller, and then it's starting to increase. So it follows that trend that I showed earlier. Okay, this calculation has been made with the with black oil correlation. Okay, so after I have that, I know that it's linear. Well, I can then say that this integral 2 from PWF to PR 1 over mu BO dP can be approximated, because we say it's linear, with the trapezoidal rule. Okay, the trapezoidal rule says that it should be, because remember, it's simply the area. If you have your PWF here, and you have your PR someplace here, okay, it's going to be simply the area under this curve. And to approximate the area, remember, you can use the trapezoidal rule, which tells you that essentially, well, it's just this rectangle this rectangle number A, okay, plus number B, plus this triangle. Okay, that's what you say to calculate the area. And then this will be PR minus PWF. And here, something that we are very happy that we got the difference in the drawdown. This is the drawdown times, and then we have to evaluate 1 over mu BO at PWF plus 1 over mu BO at PR, okay, times 0.5. But this term, okay, instead of evaluating into pressure, because it's a linear relationship, I can simply say this is 1 over mu BO at P average, where P average is PR plus PWF divided by 2. Okay, all of this, okay, because it's linear, so I can say simply that's equal to that part. So then I find out that that integral 2 is equal to PR minus PWF divided by mu BO evaluated at P average. Okay, then I can go back to my expression, to the full expression, to the IPR expression, and I find that so is a to the left was ln of RW minus 0.5 equal to 2 pi kh divided by QO, and PR minus PWF divided by mu BO at P average. I think so. Let me see if I'm taking it properly. Taking everything in. Okay, and then I can just clear the expression. Remember, the IPR expression is QO equal to some PR minus PWF. And here I have what is called the J, which is 2 pi kh divided by mu BO at average times the ln of RW minus 0.5. Okay, and then all of this is my J. And you see, it actually fits quite nicely with the previous. I have a J, which is constant, okay, relatively constant. That is a proportionality constant between the drawdown that I have here to the right and then the rate of oil at standard conditions. Okay, the only thing is here, this one, you see it depends, it's a bit, depends is average, so it's at this average pressure and temperature. So this might not be, we will see in the next video if how constant this is. Okay, but you see, for example, if you increase permeability by 10%, okay, or if the permeability is 10% higher, that means that then you get directly 10% higher J and 10% higher in Q. Okay, the layer, let's say, is thicker, is high, has a bigger thickness, so then it's also going to improve that. Okay,